Hello, everyone, and welcome. Thank you for attending. My name is Kristen Neath. I am the Canadian National Sales Manager with Kinetics Noise Control for our commercial, industrial, and environmental markets. Today's webinar will be going over understanding and reducing air system noise. So an overview of the topics we'll be going over today. First of all, we'll be going through airborne noise and sound in an HVAC system. This will be going through some of the science and theory. Next, we'll show a couple examples of a duct system acoustic analysis. There will just be a brief introduction to duct silencers and how they work. And then lastly, we'll be locating these silencers on an HVAC system. Please feel free to leave any questions in the question bar of the webinar here. If there is time at the end, I'll try and answer them. If not, I will reach out to you directly after the webinar to answer your questions. So noise and sound. Noise is any unwanted sound. Sound itself is energy that propagates itself as a wave, and it either travels through a fluid or a solid. In a solid, it's transmitted through the building partitions, and this is felt as vibration. This would be mitigated through vibration isolation. In a fluid, the sound is transmitted through the HVAC system, and this is the airborne noise and what we're going to be discussing today. If you look at that image on the left of the slide there, that's a typical school layout. That yellow box there, that's the mechanical room, that's the source. That's where all the noisy equipment is. The green boxes there, that's your library and a classroom, corridor, office. These are the receivers. These are the people who are going to be hearing that noise from the mechanical room. And those blue lines, they are the path. That's how the sound travels from the source to the receiver, and that's the ductwork, and that's what we're going to be talking about today. So we're going to look at each one of those components individually. So starting with the sound source, this is going to be probably a fan, so an air handler or a rooftop unit, something like that. And there's either going to be a vibrating surface or a turbulent airflow. This surface or this airflow is going to excite the air particles, and they're going to generate a sound wave, which is just a variation in air pressure below and above atmospheric pressure, and that's the sound wave. The rate at which these sound waves or acoustic energy is emitted from the sound source is called the sound power. This is the rate at which acoustic energy is released from a source. It's a fundamental property of that piece of equipment, so it has nothing to do with where the receiver is in relation to the sound source. It has nothing to do with any of the environmental factors around the sound source either. So some of the characteristics of the sound wave that's being emitted. Number one is the frequency, or what you might hear as pitch. We measure this in hertz. And this is just how often we see that difference in air pressure over a period of time. For HVAC noise control, we're quite often dealing with 8 different octave bands or 8 different frequencies. That's 63, 125, 250, 500, 1000, 2000, 4000, and 8000. Along with the frequency, we also want to consider the wavelength. And the reason the wavelength is important to consider is because, let's start by looking at a 63 hertz wave. The wavelength at that frequency is going to be about 18 feet long. Alternatively, if we look at the wavelength at 8,000 hertz, that wavelength is only going to be about an inch long. So the noise control measures that we'd have to take to control a low frequency noise versus a high frequency noise is likely going to be quite different. There's 2 main types of sound, so one being tonal, and this is not very common on an HVAC system. This is a simple wave. All of the acoustic energy is located at one frequency. What's far more common is broadband sound, and this is a complex wave. There's going to be acoustic energy across pretty much all of the frequencies. Where that energy, or the octave bands that have most of that energy, is going to depend on the piece of equipment it is. So looking at these charts now, these start at very low frequencies, that 8 hertz to 32 hertz. That's going to be a throb. That's not going to be something you hear. That's going to be something you feel. And it's not something that typically comes up on a typical commercial HVAC system. As we get to those higher frequencies, so the 63, the 125, the 250s, this is going to sound like your rumble, your roar. This is going to be your fan noise. It'll come from larger units like an air handler, a makeup air unit, a rooftop unit. So you're going to see the majority of the sound energy, or the biggest sound power numbers, in these frequencies here. As we get to higher frequencies, for the 250, 500, 1000, this is a hum, a buzz, a whine. This is generally smaller pieces of equipment, terminal units, VAV boxes, fan coil units. And as we get higher, so the hiss, the whistle, that's going to be diffuser noise or air rushing. So let's talk about the receiver. So that acoustic energy is being emitted, those sound, that sound wave, those variations in air pressure. And so those variations in air pressure, they impart a force on our eardrum, and that's how we hear. So that is the sound pressure. So unlike the sound power, this does relate to the receiver's position relative to the sound source. It does take into consideration the absorptive characteristics of the things around it. I like to relate this to an electric heater to make it a little bit easier to understand. So you have an electric heater plugged into the wall. It's going to emit a certain amount of heat energy, whether there's someone there or not. You walk into the room, and as you get closer and closer to that heater, you're going to feel more and more warmth. And that's the same as sound pressure. You get closer to the sound source, you're going to hear more and more sound, but that unit or that sound source is always going to be emitting the same amount of energy. So if we compare a couple of things here, so let's look at these two charts. First one being sound power. We measure this in watts. We compare a human breath to a space shuttle launch. You can see there's quite a vast range there in terms of the sound power. Same thing for sound pressure. We're comparing the threshold of hearing to a military jet, very large range of numbers. To make those numbers more manageable, we put them on a logarithmic scale. So you can see in the middle of the screen here, there's an equation. We use that to convert our sound power to a logarithmic scale. So we take a measured value over a reference value, the log of that. We assign that the units of bell. We multiply it by 10, and that's how we get the unit of decibel. So we do that for both sound power. We know there's a relationship between sound power and sound pressure, so we apply a similar equation for that. And we put them both on a logarithmic scale. And you can see here now, looking at sound power, we have a difference. We're going from 10 to 200. And those numbers are going to be a lot more manageable and a lot easier to work with than working with sound power in watts. Same thing with sound pressure. We're now looking at a range from 0 to 140, which the numbers are going to be a lot easier to work with. So what does a decibel sound like? What is one? So 1 or 2 dBs, it's going to be negligible. You're not really going to hear a significant difference at that level. As we get a little bit louder, so plus or minus 3 dBs, you're going to be just able to perceive a difference in the sound levels. Obviously, as that difference gets bigger, you're going to notice a bigger difference. So plus or minus 5 dBs, it'll be louder or quieter. Plus or minus 10 dBs is normally when we say it's going to be half as loud or half as quiet. And as we get over that plus or minus 10 dBs, it's going to be much louder or much quieter. So because we put our levels on a logarithmic scale, we can't do linear math anymore. We have to do logarithmic math. So let's look at the top chart here. If the first column on that, we have two sound sources that are very similar. So they're either the exact same sound levels, or one is 1 dB greater than the other. Instead of adding those together and doubling it, we're actually going to only add 3 to the bigger number. So if you remember from the previous slide, a difference of 3 dBs is just barely noticeable. It's just able to be perceived. I like to compare this to standing on the side of the road, seconds, and then two cars drive by. If you compare how loud it is for one car versus 2 cars at the same time, you're going to say that's not twice as loud. It's just going to be a little bit louder with 2 cars versus 1. As we move down the chart there to the column on the far right, we have 2 significantly different sound sources. So what this is telling us is that if we have 2 sound sources that are very different, we're only going to hear the much louder sound source. The quieter one becomes insignificant. So this is like being at a rock concert, right? And you have a friend next to you who's trying to talk to you in a normal speaking voice. Number 1, you're not going to be able to hear a word they say. Number 2, they're not going to be contributing to the overall sound levels at all, because the rock concert's going to be so much significantly louder than that speaking voice. So anytime we want to fully describe a sound, we need to have both a sound level and a frequency. Now, quite often, no one wants to deal with 8 different numbers at once. So we use a way to condense those numbers and turn it into one, and that is the noise criteria, or NC level. This is the most common method of dictating noise requirements in an indoor space. And what it is a series of curves, and these curves dictate the maximum allowable sound pressure at each different frequency. So that chart on the right there, you can see we go from NC 60, which is the loudest, down to NC 20. And the way that this works is we would take the sound pressure levels of the space, we would plot them on this chart, and what we're looking for is the lowest or the quietest curve that does not intersect with the room sound pressure level plot. So in this case, the example that I'm showing here on the right of the screen here, this room would actually be NC 50. Now, if that's an acceptable sound level, that's great. If not, we'd have to put some noise control measures into the system to reduce the room sound pressure level and bring it down to the acceptable NC level. Okay, lastly, we're going to talk about the path. Now, you can see in that image on the right there, there's 5 different sound paths. These are the most common sound paths on an HVAC system. There's the structure-worn path through the floor. We have the path through supply. We have the duct breakout, which we'll talk about in a few minutes here. But basically what that is the sound energy breaking out of the duct before it reaches the terminal. We have the return path. That's the sound path, sound traveling from the fan through the return duct. And then there's the sound path through the mechanical room wall. So the radiated noise from the unit traveling through the wall into the occupied space. So Kinetics has solutions for each one of these sound paths, but today we're going to be specifically focusing on the 3 that are highlighted there. That's going to be the supply, the return, and the breakout path. The reason the sound path is important is because each one of the duct elements that the sound energy encounters ends up offering some sort of natural attenuation. So it naturally takes some of the sound energy out of the system. And this can either do it by a little bit of vibration or reflection or branching. And we're going to go through each one of these relatively quickly just to show you how they affect the sound levels. So starting with unlined duct. So what happens is the sound energy inside the duct, some of that energy is transmitted to the duct surface. So this is a function of the shape and the size of the duct. Depending on the surface area, will have more or less natural attenuation. And what happens is just a negligible amount of vibration that dissipates some of that energy. If there's quite a bit of duct or long duct runs on a system between the source and the occupied space, we can see a pretty significant amount of attenuation. Keeping in mind that you're not going to see the same thing with circular as you will with rectangular. Rectangular is going to be a lot more effective for natural attenuation than circular will, just because of how rigid a circular duct is. Next is line ductwork. So line ductwork is going to be just as good at unlined for attenuating those low frequency noises. We're not going to see any additional natural attenuation from this line ductwork. And the reason for that being, if we remember back to a few minutes earlier when we talked about that wavelength, those low frequency wavelengths are very long. They're many feet. A 1 or 2 inch thick piece of duct lining is going to do nothing for that 18-foot long wavelength. Where this line ductwork is really effective is in those mid to high frequencies. The line ductwork is really effective using it with in-branch duct element like a VAV box, something a little bit smaller where a lot of the noise or the sound energy is going to be in the mid or higher frequencies. So I'll take this opportunity to talk about duct breakout for just a second. And as I explained before, duct breakout is when there's too much sound energy in the duct and it ends up breaking out of the ductwork. Now, if this is over top of an occupied space, that could be a concern. It could affect the overall noise levels. So the ways that we would mitigate this is, number one, we would reduce the amount of sound power in the duct before it reaches an occupied space. That would be putting a noise control device before it enters that to reduce the sound levels. Or alternatively, we can increase the thickness or the mass of that duct by increasing the gauge of it to better be able to hold in that noise. Next, we have elbows. And so what happens here is there's a little bit of reflection that happens of the sound wave off of the back of the elbow there. That reflection can naturally attenuate some noise. If we have quite a few elbows on a system, it can give some pretty significant natural attenuation. And depending on the type of elbows they are, whether it's a radiused or mitered or turning vanes, lined or unlined, each one will be a little bit different. Next is branching. Now, this is probably the most significant mechanism for natural attenuation. And the reason for that being is the same way that the flow is divided through different branches. That sound wave is divided in the same ratio. So it really can give quite a bit of natural attenuation to the system. And lastly, there's end reflection. So this is when we have, the duct is terminating through a diffuser. The sound energy expands very rapidly from inside the small duct into the space. So when that rapid expansion happens of the sound wave, there's a little bit of incidental reflection that happens, and we can get some pretty significant low frequency attenuation through this end reflection. Now that we have that sound energy into the room, we're going to convert that to a sound pressure. We're going to consider the size of the room. We're going to consider the absorptive surfaces. That equation on the right there is for a typical office classroom type, based on the size and the furnishings in a room like that. And this is when we convert it to a pressure level to figure out what the actual NC level is in the room. So when we start doing an analysis, these all start to come into play. So first of all, we're going to determine the most sensitive space on the HVAC system. So this is either going to be the room that's closest to the sound source, so has the shortest path between the source and the room, or it could be the most sensitive space. So let's say the room closest to the sound source was a closet or a storage room that's not commonly used. You might want to consider doing an office that's down the hall with a little bit longer duct run, but a more sensitive space. We're then going to look at the sound power levels of the unit. So this would be making sure that we're looking at the sound power, making sure it's the dBA, or sorry, the dB, not the dBA. We don't want to use A-weighted sound levels. We then look at the sound path between the source and the receiver and look at the natural attenuation that happens there. We take the sound power that's then in the room, convert it to a sound pressure, and compare it to the NC curves. So here's an example calculation. So the red circle that's in the bottom right hand there, that's the supply side of a rooftop unit that's directly above it. That blue line is the path the sound is taking, and that red, the larger red circle is the room that we're going to analyze there. Now when we do the analysis, we're going to look at just one diffuser until we get to the end, and then we're going to incorporate all four of them. So you can see the duct elements are all laid out on the right of the screen there, the ducts, the elbow sizes, the amount of branching that's going through the diffuser, as well as the size, number of diffusers, and the required NC level for the space. So this is what a typical supply system, or it's not a supply system, this is what a typical analysis looks like. We have the sound power at the top. You can see the natural attenuation from each duct element that's there. We have the sound power level in the room, that's the PWL in room line. We convert that to a sound pressure, incorporate the multi-terminal correction, meaning that we've gone from analyzing 1 terminal to 4. And you can see that that red box at the bottom, that's how much required attenuation is needed to get the NC35. This analysis is showing us that currently we are not at NC35, we're too loud. We need to put in some sort of noise control measures to bring the sound levels down to meet the NC35. So we can do the same thing for the return system as well. So on the return system, same thing, we're taking the sound power levels. We don't have a lot of duct elements here. The difference with this one being is because it's terminating over the corridor, we're going to use that as our occupied space. Now, because it's not ducted in that corridor there, we're going to take into consideration the sound energy that's lost when it's goes from the sound energy that's lost as the sound has to travel through the ceiling tiles that are between the occupied space and the return duct there. So going through the same calculation here, so we have the sound power levels from the fan. We're deducting the natural attenuation from all of the duct elements, including those ceiling tiles. And again, you can see the required attenuation. We need an additional 7 dBs in the 250 Hertz band in order to meet the NC40. So lastly, we'll do a breakout noise calculation here. So in this scenario here, we have a rooftop unit directly above an occupied space. It's quite common for there to be too much sound energy in the ductwork directly below the rooftop unit there. So it's always important to consider whether breakout noise will be a concern directly below the rooftop here. So the way that we do this is, again, we take the sound power levels, any sort of duct elements that are in play here, the ceiling type, and again, the room criteria. Now, because we're only analyzing the duct directly below the rooftop unit, we're going to be looking at the corridor space. So here we have the analysis. Again, so we have the sound power levels. The next line down, you can see this is the amount of sound energy that's lost through the casing of the duct. The next couple lines down, this is just completing the equation with utilizing the surface area and area ratios. And then you can see at the very bottom there, that's required attenuation. We need 2 dBs in the 250 Hertz band to meet the NC40 in the corridor. Now, if you can remember till earlier on, 2 dBs is not that significant, and I don't think it'd be worth making this duct any heavier in order to hold in noise. This should be a sufficient selection. So in this case here, 18 gauge duct was required to meet the noise levels. So we'll need to make sure that that duct is 18 gauge. So here's the outcome of the analysis here. So on the supply side, we have a required attenuation from the analysis. We know that the casing gauge is going to need to be 18 gauge minimum to hold in that breakout noise. On the return side of the system, we know the required attenuation is going to be 7 in that 250 hertz band. So when we go to select a silencer or noise control product, we need to make sure that the attenuation is greater to or equal to that required attenuation that we just calculated. And we also want to note the pressure drop of the silencer, and we'll talk about that in just a minute here. So the silencer, the attenuator, the sound trap, these are all words that are used to generally describe the same thing. It's a silencer. It tends to be regional. I'm going to call it a silencer from here on out, but quite generally they're the same product. So what it is it's designed to replace a piece of ductwork. It comes in configurations of elbow, rectangular, circular, but you know, these are just standard configurations. It can be made of just about anything sheet metal can be made into. There's 3 performance characteristics for a silencer, and that's the insertion loss, the pressure drop, and the generated noise. So the insertion loss of the silencer, this is the difference in sound power levels in a system with and without a silencer. It's how much sound energy is taken out of the system by the silencer. We measure this in 8 different octave bands, just like we do the sound power and sound pressure up until now. Next, we have the pressure drop. Now, this is the consequence of putting a silencer in the system. The silencer creates an obstruction. You're going to get a little bit of turbulence. You're going to get some pressure drop associated with putting the silencer in. And last one is generated noise. So again, by adding that silencer to the system, it does create obstruction. There will be some turbulent airflow. There will be some noise generated as the air passes through the silencer. This is called generated noise, and in most cases, we don't need to consider it, but I'll speak about that in just a couple slides here. So the way the silencer works is, first of all, this is a cross-section of the silencer here. Those shaded areas are what we call baffles. That's where we have the acoustic media. That's where all the sound gets absorbed. So the air enters into the silencer here. There's a little bit of turbulent airflow that happens just as that air hits the baffle. The air is then compressed as it enters into the silencer, and we get a small amount of insertion loss just from some reflection that happens there, and a little bit of pressure drop just from the turbulence and the compression of the airflow. Next, we have the passage. So this is where the sound energy enters into those baffles. The air is compressed, it accelerates, and so as the sound energy enters into the baffles there, the sound energy rubs the acoustic media, excites it, rubs together, that sound energy is dissipated as a very negligible amount of heat energy. And then we have a little bit of pressure drop through here too. There's pressure drop associated just with friction losses as the air travels over the baffles. And lastly, we have the outlet. This is where the air redistributes back to the size of the duct. There's a small amount of low frequency attenuation here, just as the air redistributes back to the size of the duct. But this is where we're going to see most of the pressure drop. So that's why you can see the slight taper at the end of the baffle there. That's the pressure regain tail. It reduces the amount of pressure drop the system can experience due to the silencer. So let's talk about generated noise again for a second. So like I said, this is the noise that's generated when the air flows through the silencer. We would consider this another sound source on the system. Now, remembering back when we talk about 2 significantly different sound sources, you only hear the louder one. And that's quite typically the case when it comes to generated noise on a standard commercial system. So typically the fan sound power levels are typically much greater than the generated noise from the silencer, so the silencer generated noise becomes negligible. There are times when we do want to consider the generated noise, and that would be for when we have very quiet systems. So let's say NC20 or lower, this is going to be a performance space, a recording studio, something of that nature. So the way that we control the performance of a silencer, either through the open area or the length of it. So the bigger the open area, the lower the pressure drop, but it's going to have lower insertion loss. The smaller that open area, the better the insertion loss, but the lower the pressure drop. The length is very good at controlling the noise as well. And the reason for this being is, number one, as we increase the length of the silencer, it's going to make it longer and better able to attenuate low frequency noises, remembering that those wavelengths are very long. Also, it can add some extra insertion loss without having too much pressure drop. As the air is going through the silencer, it's only experiencing a small amount of friction losses, so you can get more insertion loss with less of a pressure drop happening. As I said, there's 3 different standard silencer configurations. A rectangular silencer, these are very good for just about anything, especially long duct runs or chases. There's a lot of variations in the way the baffles are configured, so you can usually find a good trade-off between attenuation and aerodynamics. Next is an elbow silencer, and these are generally used when a rectangular silencer just won't fit. There is more pressure drop associated with them, so we tend to recommend them for lower velocity applications. And lastly, circular silencers. These are good for mainly two different applications. Number one is high velocity applications, and the reason for that being is, if you see on the picture on the bottom right there, all the acoustic media is outside of the silencer. So there's very low pressure drop associated with it because we're not obstructing the airflow at all. The other application these are good for is when there's round ductwork, just to match the shape of the duct. Now you can also see if we do need a little bit more insertion loss, the silencer on the right there does have a bullet in the center of it. That gives extra attenuation, but there will be more pressure drop associated with it. So like I said, we are not limited to just those 3 configurations. Here's a few examples of some other options we have, whether it be extended casing, round end caps, T-shaped, crosstalks, anything that we can make out of sheet metal, we can turn into a silencer. So very quickly, I'll just go through these last couple slides regarding locating the silencers on a system. So whenever we're locating silencers, we want to take into consideration 2 different factors. Number one is acoustics. We want to make sure we're placing the silencer to prevent any break-in or breakout noise. Number 2, we want to make sure that that location we found for acoustics is going to be good for the aerodynamics as well. And that brings us to pressure drop. So, to system effects. When you look at the submittal for a silencer, the pressure drop that's listed there is under ideal conditions, meaning that it was tested with 3 straight duct runs before and 3 straight duct runs after. As you probably know, that very rarely happens in real life. So we need to make sure we're taking into consideration the conditions before and after the silencer and how they could affect the overall installed pressure drop of the silencer. So what we do is we apply a factor to the condition before and the condition after the silencer to get the installed pressure drop. So in this example here, the silencer submittal pressure drop is 1/4 inch, so 0.25 inches. The upstream condition, this is an outside air intake silencer. We have a sharp, abrupt entry where the air is entering through that louver there, and that's about 1 duct diameter away. We assign that a factor of 1.1. The downstream condition here is a radius elbow about 1 duct diameter down from the silencer, and we assign that a factor of 1.2. So you can see that the total pressure drop of the system here once that silencer is installed is 0.33 inches. So when it comes to locating these silencers on a system, the first recommendation is always on the inside of the mechanical room. Usually the system effects here are relatively good. It can guard against any sort of break-in noise, so there's a lot of mechanical loud equipment in this room. The silencer can clean that up if any of it has broken into the duct before it enters into the occupied space. And quite typically you can use a standard rectangular silencer here. The next location we recommend, if it doesn't work inside the mechanical room, is on the outside of the mechanical room. In this situation here, the only consideration you might have to make is number one, the only considerations you may have to consider are one, you might need to do something a little more custom with the design of the silencer based on what the ductwork layout is. And number two, there's a breakout noise concern here as well. The silencer is now over top of a occupied space. We might need to use a heavier gauge casing to make sure there's no breakout noise. And lastly, if those two locations aren't working, you might want to consider doing in-branch ductwork. Now this is beneficial because here you can use two smaller silencers as opposed to a large custom one. But again, you have a piece of duct between the mechanical room and the silencers that's been untreated, and breakout noise could be a concern. I want to thank you very much for your time today. I'm sorry I went a few minutes over. Please feel free to leave your questions in the webinar box there, and I'll be happy to follow up with you afterwards. Thank you again for your time.